Okay, thank you. So this is joint work with Jonathan Huggins from MIT. You can talk to us both at the poster afterwards. So I'm just going to start by posing a problem, and I promise you eventually this is going to become Frank-Wolfe, but first let's just look at this problem. So we're going to be interested in a saddle point problem. So we have some function L. You should think Lagrangian, not loss function. So we have some function L of u and theta. And we're interested in minimizing over u and maximizing over theta. And we're actually going to assume that it has the following form. So it's some arbitrary convex term that can depend on u. And you have some arbitrary concave term that can depend on theta. And then the restriction we're going to make, the main restriction, is that the interaction between u and theta is bilinear. So I wrote this as just the standard inner product, but this could be any bilinear function. It doesn't even have to be positive definite. And to eventually tie this into optimization, we can think of sort of maximizing over theta, and then we'll just get a single variable, and we'll get this decomposition as h of u plus r star of u, where r star is the Fenchel conjugate, which is basically just, by definition, it's the maximum of this term over theta. So if you, I guess Francis will be talking later about duality between conditional and subgradient, and in his paper, a very similar decomposition appears. So earlier at the poster, someone asked a very good question, which is, why should we care about this problem? So here's a bunch of problems that can be cast in this framework. So first, you get LPs pretty straightforwardly. So if we make if we just make everything linear, so H is C transpose U, R is negative B transpose theta, and then we have U transpose A theta as the interaction term, then it turns out that what we get is we just get a standard LP. We're maximizing C transpose U subject to the constraint that AU is less than or equal to B. And just as easily, we can get a QP. We just add a quadratic term to H. We can also get SVMs. So here it's a little bit more complicated. But basically, we get the quadratic regularizer term. And then we have a sum over our training examples. And here's sort of the margin. And then we have some sort of weights on the costs. And we're going to constrain these weights to lie between 0 and 1. And then you can show that what you get is actually the hinge loss, just like you would want. And then finally, you can also do Lasso. It sort of corresponds to having an L1 regularizer, your residual term, and then a dual term with an L2 regularizer on the dual. So don't worry. If this is mainly just to demonstrate that you should care about this problem. And maybe for those of you who think about Lagrangians all day, it was a nice review. So now let's talk about how to actually solve this problem. This is the main point of this talk. So just a reminder, this is the function we care about. I'm going to leave that up the whole time, so don't worry. And let's just try something. Let's just try sort of the first idea that might come to mind, which is, well, here's this 2-argument function. We want to optimize it. Let's just do something like EM. So what would that be? That would be, let's fix theta, minimize over u, and then we'll fix u and maximize over theta, and then we'll sort of repeat that. So you could think of this as like the most greedy thing you could ever do, right? We're just going to sort of iteratively pick the best response, but this doesn't work. So there's actually a very simple counterexample where you get oscillation. You just make everything in one variable. H will be quadratic, R will be quadratic, and then we can work out everything in closed form. And basically, we'll see that these updates make u equal to negative theta, and then theta equal to u. And so you're just going to oscillate back and forth between the negative and positive value. And actually, if you made these slightly less than a half, if you made this like 1/3, then it would be even worse. You'd actually spiral off to infinity. So this is sort of maybe the thing you might want to try, but it doesn't work in general. Even if everything in sight is sort of nice, strongly convex, strongly smooth. So we're going to try something slightly less ambitious. And so the slightly less ambitious thing we're going to try is, instead of doing minimizing relative to the last step, we're going to change this very slightly. And what we're going to do is when we do the theta update, we're going to update relative to the average of all of the u's so far. So we have this ut hat term. It's just defined to be the average of everything so far. And it turns out that now, if we do this, we'll be fine. So the theorem in our paper is that as long as R is strongly convex, then these iterates are going to converge to the optimum, and they're going to converge at a rate of log t over t. You might be wondering what the log t is from. Well, it turns out that what we'll see at the end of the day is this corresponds to doing Frank-Wolfe with the wrong step size. So if you're willing to replace this with a weighted average and get the right step size, then you get O of 1 over t convergence. So you get what you would want. And there's basically an analogous algorithm where instead of R being strongly convex, if H is strongly convex, we're also fine. The only difference is we average over theta instead of U. So we have two algorithms, and they both have primal dual convergence. OK. And now I promised that I would get back to Frank-Wolfe. So it turns out that Frank-Wolfe is just a special case where H is equal to 0. So when H is 0, what are our updates? So U is just going to be, we're going to minimize this part. H is 0, so we're just minimizing U transpose theta. And then the point is that theta, so this is the real key step where the key tie-in with Frank-Wolfe. So theta is going to be the argmax of U transpose theta minus R of theta. And the key point is that this actually simplifies to the subgradient of the Fenchel conjugate of R. So I won't go through that computation right now, but this is sort of a standard result about Fenchel conjugates. These are also called convex conjugates. And so this is why we get the update, because if we sort of plug this in up here, then we end up with exactly the standard conditional gradient update. And then in general, we get these updates. So we have U is the subgradient of the Fenchel conjugate of H, and theta is the subgradient of the Fenchel conjugate of R. A key point, so our convergence results said we needed R to be strongly convex. That corresponds to R star being strongly smooth, which is the condition you need for Frank-Wolfe to converge. And one nice thing is now H, you can sort of add in non-strongly smooth H terms as long as you can sort of compute this map, which looks sort of basically a proximal map. And another nice thing is that this looks much more symmetric than sort of the standard iterates. And in addition to sort of these LP and SDP, or LP and QP algorithms we talked about earlier, it turns out that using various decompositions, you can get sort of a lot of nice, more complicated algorithms. You get Frank-Wolfe that can handle L1 penalties. You sort of re-derive this low-rank SDP algorithm by Aurora, Hazan, and Kale. And then we also have some generalizations of herding, and you can see these all at our poster. All right, thank you.
So the poster is right over there. And are there any questions?
Yeah.
Yeah, back to the slide with the equivalence to Frank-Wolfe.
Mm-hmm.
Are there constraints on U?
So sorry, I should have said this earlier. So we're implicitly assuming that U and theta are constrained to some convex set. For Frank-Wolfe to work, you sort of need it to be a compact convex set.
Right, I mean, you could incorporate the constraints into H, but...
Right, so yeah, I guess the other thing is for what I said about Fenchel conjugates to exactly be true, really you need to incorporate it into H when you're computing the Fenchel conjugate. So you can do that by just adding sort of an infinite barrier at the edge of the constraint set. Yep.
So how does this relate to solving like matrix games? Like for example, if H and R were just 0 and you're minimizing, maximizing over it.
Yeah, so that's a really good question. Robert asked this as well at the poster. So basically, so let's go all the way back to the beginning. So well, let's just go to here. OK, so matrix games would correspond to basically H and R are both 0, but you need A to be some payoff matrix. And if you just try to do that, you're going to be in trouble because you have no convexity anywhere. So there's sort of, you know much more about this than I do, but basically there's this family of techniques that basically involve smoothing the game out, which corresponds to artificially adding either one or both strongly convex terms, and then letting the degree, sort of letting that scale to 0 as time goes on so that you get the right answer. Yeah?
Yeah, so there's an old method called fictitious play.
Yes, exactly. That was it. But they're both empirical distributions in that. I'm wondering how that converges. I was wondering.
So I believe there's some recent work of Ricky Vora on that. And in fact, I had a note to email him tonight to find this out and pass it on to you and your co-author. Anyway.
Yeah, so basically it's known that fictitious play converges. Our convergence results don't sort of show that fictitious play converges, but sort of smooth versions of fictitious play our results would apply to. Yeah. Cool. Yeah? Oh, are we?
We don't have more time. So I'll ask you later if we want.
OK.
Let's thank you.
Thank you.